Okay, ladies and gentlemen, once again, we're here talking about energy, and all of these little toys in front of you all represent different types of energy. And right now we're talking about how this works. This is a radiometer, and it works on the notion that when air molecules heat up, they move faster. And so we have this hypothetical sphere with air molecules moving around, bouncing off of each other, bouncing off of the sides of a container. And when we heat it up, they start to move faster. And that actually doesn't just make them move faster, they exert more force. If you guys think about them as moving objects just like this, right over there, yeah, that's what I'm talking about.
Throw it again, I'll catch it.
No, seriously, you guys, be quiet while I'm trying to get this idea across. I know it's sort of Friday for you guys. But when you heat this up, let's say this was a balloon with elastic sides, they're not just going to move faster, they're also going to exert more force. And that causes the thing to expand, because when they move faster and exert more force, they take up more space. And so that is actually going on here also. When, where's the orange? Dang it. Here it is. When the radiometer heats up, the black side absorbs more heat, and that causes the air molecules behind it to start to move faster. See, before this, they were static because the air molecules were exerting the same amount of pressure on both sides. And so they're hitting it on this side and they're hitting it on this side, and it's not going to move. But once the black side starts heating up, the air molecules on that side start to exert more force, and they're going to be, in my terrible drawing, exerting more force here and cause this thing to start to spin around in this direction as more force is exerted on the black side, and it moves. So that's how a radiometer works. So that's heat energy causing an increase in kinetic energy, thermal energy causing an increase in the kinetic energy of the air particles, causing them to move faster. Okay, let's see. Let's talk about what other kinds of energy do we have here. How about this? Somebody tell me, like these two. What kind of energy are we talking about? Electricity, right? And so this is actually electricity being converted into light as the electricity converts the air molecules into their plasma form. This is a plasma ball. Plasma is our fourth state of matter, where atoms are so energized that they actually lose their electrons and become plasma. It's the relatively unknown fourth state of matter that people think is just a science fiction thing, but it's not.
How much does one of those cost?
I don't know. I got it for Christmas. It was probably it's probably like more than 5, less than 50. It would be my guess.
More than 5, less than 50.
I don't know. I got it for Christmas. I have no idea. Both of these I got from my brother, who always buys me these little things because I'm a science teacher, and so he got me these geeky things. And here's another thing. This is powered by electricity also. Electromagnetism. Electricity and magnetism go together. They're two sides of the same coin. You can't have one without the other. But that definitely is capable of doing the work of holding up this sphere. Oh, you didn't notice that before until I did this? Yep. Anyway, and then what other kind? You could do a lot of conversions from electrical energy. We're very good at them. What does this convert electrical energy into? Heat, right? Very good. So we've got electrical energy converted into light, basically converted into a force generating apparatus, and into heat. All right.
What's the mousetrap?
What's that?
Mousetrap.
Oh, wait, hold on. Before we get to the mousetrap one, I forgot one. We'll talk about that in a minute. Here's another kind of energy. It doesn't have anything to do with the mousetrap. I'm just putting it on a pedestal. What kind of energy are we talking about there?
Chemical.
Potential, chemical. Both are correct, because chemical energy is a form of potential energy. Actually, it's a little bit of a misnomer, misnamed, because coffee doesn't actually give you energy. Coffee signals your cells to start burning stored chemical energy. Each of your cells has glycogen in it, which is animal starch, basically. It's like starch, but it's the kind of starch we have. And when you drink coffee, it doesn't, the caffeine molecule doesn't give your brain energy. It signals your brain to signal your body to start burning its sugar storage. And so that's why you get more energy when you drink caffeine, because your body's burning its stored starch energy. But anyway, yeah, okay.
Does that mean that if you drink a lot of coffee, the caffeine, if you burn enough energy, you'll lose weight? Not
Probably not, but I don't really know a good answer to that. I think that, I mean, caffeine is a very popular ingredient in a lot of, like, stimulants are a popular ingredient in diet pills, and so maybe. And also it makes you pee more, which is going to make you lose weight also.
But mainly the only thing it would like motivate you to go for a run or something.
Maybe, if that's going to do it.
Gives you
But, you know.
energy, it gives you energy and then it, like, you like crash.
Right, that's the thing, is it gives you energy and then you crash. You'd be better off just doing the exercise.
If
It
you drink
actually
that
gives
much
you more
coffee when
energy
you get a
long term.
medical condition,
What's that?
if you drink that much coffee when you get a medical condition,
How much coffee?
I mean, if you suck enough coffee to make you
Enough coffee to get me up and exercising would give me a medical condition. But I'm a kind of sedentary person. Let's move on.
I feel like
When I talk about chemical energy, potential chemical energy, I'm talking about any situation where you've stored energy in chemical bonds and it can be released, and we've now converted chemical energy into heat and light. And so this is true for gasoline, this is true for food, this is true sort of for caffeine. That was just my little symbolic gesture towards chemical energy. Okay, excuse me. Right? Okay, so yeah, all right. Let's talk about this. Let me move this aside. Turn off the plasma ball. Turn this off. All right. So we have this. This is a Havahart trap, and this basically works according to what force which can exert energy? Gravity. Gravity creates potential energy. Yes. Well, you were right on that. You were right. And it's very simple. You store potential energy by pressing down on this lever. I exert a tiny amount of weight, and that stores these doors in the open position. It's held in place by a tenuous little lever that's attached to the tray here. And when the tray gets, when the mouse comes in to eat the bait which you put on the tray here, and he steps on it, it causes this to close. And if you have these set up the right way, then it'll stay closed and the mouse gets out. Does he ever die? Only if you.
see why you never.
That's a really
caught
big
the mouse
trap.
before.
I did catch the mice. I did catch the mouse. I finally did catch the mouse.
Twice.
Twice, 3 times, yeah, but I finally caught him and let him go outside. Anyway, so that one works on energy. What kind of energy do the other kind of mouse traps work on? Okay, springs, potential springs. Springs, believe it or not, are an accepted, quantified, meaning there's formulas attached to it, form of energy. Let me put this down. I feel like I can't be seen. You're not getting my best side. I hope this isn't my best side, but anyway. This is my bad side, people at home. Anyway, no, they're all suspended anyway. let them look at my bad side. Yes, springs, folks. Springs are a quantified way to store energy. And where it is. I just said that. Where is it? Okay, folks? Doesn't seem like much energy, but I put energy into this system and it's stored as potential energy. Normally we think of potential energy as like, you know, the old moving, where's the black marker? We have a ball up on a hill, bowling ball, let's say, and we lift the ball up here, and that gives it potential energy. We're going to talk about that. Let's talk about it right now. Then we'll talk about the springs, because the springs are the fun part, actually. So we have a bowling ball here. Well, just since it's homecoming weekend, we'll what energy is the ability to do work, right? The kind of work this thing's going to do. Once I set this in motion, what kind of energy is it going to have? Kinetic energy. Right now, it just has potential. But when it was down here, did it have potential energy? No potential energy because it's at ground level.
Stop.
If it had potential energy, it doesn't now. It's at
How do
rest.
you get it up there?
And once you put in work, so I have to put in work to get it up here. Lift the bowling ball up, put it up there. Might not be much, but now that energy is stored. It can be stored by position. It can be stored in chemicals like the match was, or it can be stored in a spring. So I put a small amount of work in here, and it locks this spring into a compressed state, which really does hold energy. Believe it or not, okay, E equals mc squared, energy equals mass times the speed of light squared. That's a lot of energy. So the mass of something times the speed of light squared tells you how much energy is embodied in that matter. This is Einstein's, this is the equation that almost everybody knows, and it relates to the power released by nuclear reactions and things like that. But what it also means is that mass and energy are somewhat interchangeable. Actually, probably completely interchangeable, we just don't really know how. But I'll tell you this. If I had a good enough scale, okay, I compress this spring. I put energy into it. What happens to the mass of this system? Believe it or not, it goes up. If I could measure it, I put a little bit of energy into the system, which means energy plus, 0.00000.01 units of energy. That means the mass is going to go up plus a tiny, tiny bit of energy. That's just an interesting factoid. But okay, back to the springs. I have energy stored in here, and when I want to release it, the spring will uncompress. Let's have a better example. Right? Here is a. Put my finger in it. Is that what you said?
Just demonstrate.
Just to demonstrate.
Let's just see how much pain the
I mean, it'd be like transferring energy to potential.
Yeah, to my finger. That's great.
Josh, why don't you do it now
Who
that
wants
you've
to be
been
a
tasered?
volunteer?
Yeah, I think you should try taser.
Oh, gotcha.
Okay, so
Yeah.
so I compress the spring, and I put energy into that system, right? And so it takes. So this thing ain't gonna. This thing here. I've got another one. This thing could sit here for 1,000,000 years like that, and it's never gonna just do this by itself. Okay. So in order to be able to exert this mouse-killing force, it has to. Right. That's why I use these. I mean, come on, folks, have a heart. But in order to be able to exert this force,
That's all.
you have to actually put the energy into it by.
Yes.
And then we got it. And so, and here's the thing: which has more energy, this or this? This. You can tell because the spring is bigger, the spring is thicker. You can't see the spring, but it's one of those dinky little pen springs, right? And so the point is, the amount of force you have, the amount of energy you have to put into it, is directly related to the amount of energy you can get out of it. Now, let me ask you another question: which has more energy, this or this?
Whoa there, is that for a rat?
Right? It is a rat trap. And so, I need a volunteer. No, I'm just kidding.
Well, we're gonna do it over
Well, we are going to do it. Oh, see, and look at this. Not only does this have 2 springs instead of 1, but this spring is much bulkier, much thicker, and it takes a lot more energy, and it's much more terrifying to me to hold this thing. Oh, God.
Careful there.
These things are so sketchy as far as the mechanism. Oh, they scare me so much. Now,
That's all. Not of these things.
I feel like we should launch something.
Yes.
Do it.
Yes.
Launch that car.
Launch the car. What a fabulous idea.
It's gonna fly backwards.
Yeah, I think that you're wise.
All you gotta do is
Okay, we ready? Woo! Nice. That's awesome. It did not break the pencil. Oh, but it did dent it. Dented it. Okay, so. Oh, so terrifying. I feel like,
doing this for
We should try to break something.
Hey, use this plastic roller.
What's that?
Use the plastic roller.
We'll see if we can break the plastic ruler.
Yep.
Wow! Pretty impressive. That's gonna look good in slow motion, I have to say. Oh, I can go all Bill Nye. Wow! 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 See, I told you he was irritating, right? You guys didn't believe me. You're like, no, we love Bill Nye! No, we don't. Okay, anyway.
The third time's the charm with that.
The third time is the charm?
Yeah.
What are we gonna do this time?
And
My hand? Yeah.
put your hand in that.
It's the apple, okay. The apple will be our surrogate rat, and then that'll basically be it. We're gonna have to go really soon.
A feather.
Let's see. Oh, by the way, let me mention. Oh, why can't I do this?
iPhone.
Oh God, it's terrifying.
Yeah,
Ah.
An iPhone was shattered.
Yeah, somebody want to put their cell phone up here? Collegiate high school students, by midday tomorrow, or maybe even by the end of today, there will be a new study guide posted on my website. And so try to get there with your phone or something to do it over the weekend.
Monday.
What chapter? It'll be the next. I don't know how many pages. It'll say on there. It'll be the remainder of the
Chapter 6.
energy chapter 6. Yes. Hello.
The thing that we did on Wednesday,
Yes.
is there, we get to reading on the website, but is there a study guide for it? Is there
Wait, the thing you guys did in class yesterday?
Yeah, I wasn't here for it.
Oh, well, there's two questions at the end of the on the very last page.
Did
Are you in my
Did
forearm?
you get my email on the Starbucks?
Yes, I did.
Because they asked.
Okay, ready? Aww. That was Dave. I call shenanigans. I call shenanigans. Okay, anyway, folks, so let's see. What?
Seems like a hazard to be playing around with ice
You think?
He comes in tomorrow. He's got Monday. He's got broken fingers. Got a band-aid on his nose.
Sorry, Miss Nose can't come into work.
Alright, here, we'll crush the matchbox. How about that? Because it's empty anyway.
Do my arm.
Careful there. Light it on fire. That is nuts. I feel like that's a waste of.
I like the ruler.
It's a waste of empty matchbox.
Oh, it's empty?
Yes.
Oh.
All the matches are in the bag. I don't know. This must be there for a striking surface. Okay, folks. So, are there any? Oh yeah. Who knows how this works?
We learned in middle school science, and I
Oh,
forgot.
wait.
Oh yeah, Mr. Linden had one.
I know. He had 2 of them, and he made it for their like hit heads in the middle or something like that.
Oh, yeah.
Stop.
Did not.
Yeah, it-
Nobody.
Evaporation?
Temperature. Okay. So here's the thing. The red liquid is moving, but is the red liquid pushing up into there? That's a hint. That's a hint that it's a trick question to which the answer should be no. It's not pushing up into there. So what is happening?
It's pushing down.
It's being pulled up into there, actually. How?
Because the air pressure is pushing down on it and forcing the liquid to go up.
That is a nice try, but thank you for playing our game. But no. Think about it this way. What were we just talking about with kinetic energy of air? Okay, first I'll give you a hint.
Diffusion.
What has to happen before this thing will work?
Has to have the water.
Has to be dipped in water. This is a fuzzy surface, and as this cools, as the water evaporates from the surface, it cools. As it cools, the air inside does what? It shrinks. As it shrinks, it pulls up the water. And then the water goes in, dumps it back in, and it starts all over again. But here's one more thing, folks. If I dry this off, what happens? It stops moving. If I unplug this, which I have, it stops. If I don't load this, it doesn't do anything. If this doesn't have a light shining on it, it stops. What does this tell you about energy?
It needs to have a force to work.
No work in, no work out. No energy in, no energy out. That's really what it comes down to, folks, and this is the last thing I'm going to say because it's time for us to go. But think about this, folks. With energy, there is no free lunch. There is no free energy. If you want to use energy for something like driving your car, running your refrigerator, running your iPad, running your cell phone, running basically your entire modern American industrial life, there's no fuel, there's no energy, there's no output, there's no iPad, there's no car, there's none of those things. And so one of the things I want you to learn during this unit is exactly how much we rely on energy and why. Okay? Thank you very much. Let's go through